Hello. Here in lecture 15a of Differential Equations and Linear Algebra, we're going to be doing similar things to what we did in lecture 14a. We will still consider the harmonic oscillator model of a mass on a spring, but now in this lecture we're going to add damping, which means friction. So it does make it a little bit more complicated, but in a sense also a bit more interesting. We will derive, based on Newton's second law, the scalar second-order ordinary differential equation that describes the motion of the mass. We will also, as before, consider the corresponding first-order linear system in matrix vector form. We will re-emphasize the meaning of the idea of a vector field, which we introduced in 14a, and Nullclines from 14a. And since we're redoing a lot of things, we should be able to go faster, and I should have more time for Mathematica coding at the end to go a little bit more slowly through the ideas with that. Lecture 15b is linear algebra. We will compute a determinant with row operations based on properties mentioned in lecture 14b. We will find and iterate a reflection linear transformation. We'll need the idea of a projection vector, which we talked about way back in lecture 5 there, so that'll be a review. It's based on dot products to derive the formula, and then iterating it, that's the idea of a difference equation that we talked about in 14b. And then here's the big thing for lecture 15b, foundational theory of vector spaces with examples, an abstract topic that has practical importance for us in this class. All right, so let's start by considering the damped simple harmonic oscillator. We once again have a mass on a spring, but now we want to bring some friction into play. So we really are sliding on, say, a floor instead of ice. We're not in a vacuum. We have air surrounding this mass. And there's internal friction for the spring as always. Lots of friction sources here. You might think then that some sort of complicated model involving friction would be necessary. But one key thing to being successful in mathematical modeling is to try to keep things as simple as possible and see if you can get away with it, so to speak. And that's what we will do here. We will assume the friction takes on a particularly simple form. You would have to compare the predictions of the theory with reality, with experiment, to see whether the model needs to be tweaked or not. Okay, so that's a big thing to realize with mathematical modeling. Once again, we have a block with mass m in kilograms, a spring constant k in newtons per meter, and y, once again, is the displacement of the block from equilibrium. Y being positive, moving to the right from its equilibrium position, say right here at y equals 0, and y would be negative if the mass is to the left in position. Again, we assume friction is present, though we may be unsure of whether a model is going to be good because we are unsure of how friction behaves. Hooke's law refers to the spring constant K. It says the restoring force of the spring is proportional to the displacement y with a negative constant proportionality. So when y is positive, when the mass is to the right of the equilibrium, the force due to the spring is pulling in the negative direction. And when y is negative, you're to the left of the equilibrium position, the force due to the spring is in the positive direction. This negative sign takes care of both cases. We also now add our frictional force. Kind of a pun there. Instead of fictional, it's frictional. Frictional force. What is the frictional force? We are assuming, again, it takes on a particularly simple form. That it is proportional to the velocity with a negative constant proportionality. Think about that. If the velocity is positive, that means the mass is moving to the right, whether its position is positive or negative doesn't matter. The frictional force wants to oppose the direction of that motion. If the velocity is positive, the frictional force points in the other direction. On the other hand, if the velocity is negative, if the mass is moving to the left, the frictional force points in the positive direction. Once again, this takes care of both cases. The velocity is the same as the derivative of the position with respect to time, so we can write that as negative b times dy dt. Okay? Newton's second law is F equals ma, which we can write this way. Now we combine these things. We set essentially this thing right here equal to the sum of these two things right here. Of course, they have minus signs in there, so you're going to see minus signs when you add them. Here we go. Here's the first form of the differential equation. This is ma equals restoring force plus frictional force, but because they both have negative signs, you see minus signs in there. We can write this in different equivalent forms. We can add, we'll divide both sides by m, that gets us here. Then we can add k over m times y and b over m times dy dt to both sides to cancel on the right, to get a 0 on the right, and to get the same terms with positive signs over here on the left. The left-hand side of this differential equation is a linear operator, as we talked about a couple lectures ago. If you plug in a function into that linear operator, meaning take its second derivative, add b over m times its first derivative, add k over m times itself, in order to be a solution, you must get the 0 function for all time, for all t. In other words, a solution of this is going to be in the kernel of this linear operator. More on that in later lectures. We can define p to be b over m and q to be k over m to make the equation look a little simpler. But when you do put it in that simpler form, you need to remember that p is b over m and q is k over m. All these constants, k, b, and m, are all positive, so p and q are also positive. Continuing, what's the general solution of this? In the undamped case, I did write the general solution as a linear combination of cosine and sine with appropriate periods. This time, however, when you add this friction in, you could write a general solution down, but it's pretty complicated. It's too complicated for us to write down at the moment, okay? Too complicated to write the general case at the moment, at least. Though it is a linear combination of two functions, two solutions. Those solutions happen to be linearly independent. Now, I've hinted at what linearly independent means before, more than I've hinted that we're going to encounter it here. What does it mean to be for two functions to be linearly independent? It means they are not constant multiples of each other. Their graphs are not vertical stretches or compressions of each other over any given interval. That's what it would mean, okay? So just trust me on that. More on that with specific examples to come. We still will need two initial conditions. We will need an initial position and an initial velocity because we're going to have two arbitrary constants. Call the initial position y0. I could pick some specific number there. I will in an example shortly to come. Call v0 the initial velocity. Y of 0 must be y sub 0, and y prime of 0 must be v sub 0. Should make some intuitive sense that with a second order equation like this, modeling the mass, a mass in a spring, we would need to know both the initial position and initial velocity in order to be able to predict what the motion is going to be. Now let's consider the corresponding first order system of linear ODEs by defining the velocity to be dy dt. Okay? So we're essentially introducing a new variable, v equals dy dt. Now we already know about the velocity, in fact it was on the previous slide, but for the purposes of generating this first order system, in a sense I'm pretending I'm starting over. This makes sense, velocity is dy dt. That's going to be one of the equations in the corresponding system. It's going to be the top equation right here. dv dt is in the second equation. We know dv dt is the second derivative of y with respect to time. It's the acceleration. And by one of the lines on the previous slide at the bottom, that will equal negative k over m times y minus b over m times v. This is a system of first order scalar equations. We're about to write it in vector form. It's coupled. The values of v affect the values of y and vice versa. You see v's and y's intermixed in this system. What is this system in matrix vector form? We can define the vector capital boldface y, whose components are lowercase unboldface y and v. Careful, it's not in alphabetical order. It's not that I couldn't put it in alphabetical order, but we want to remind ourselves that the position is the main thing we're after in a sense. So we put that first and the velocity second. This again is a definition of dy dt, the derivative of this vector valued function. Everything here is a function of t, keep that in mind. Set these components equal to these two quantities, and that gives us essentially a differential equation in vector form. This is a system of two scalar equations here. This is one vector equation. They're equivalent to each other. As before, we can take this vector and write it as a linear combination of these two fixed vectors where the y and the v are the weights. And as I've talked about a lot, that's the same as a matrix times a vector. This particular matrix times this particular vector, because by definition, this matrix times this vector is a linear combination of the columns of that matrix with these components as the corresponding weights, which is exactly what you see here. I'm going backwards from the usual approach. We can give this matrix an A and call it capital A, and again, this vector is called capital boldface Y. Okay? So we can write it as that, and that's what ultimately leads us to the idea of a vector field. Okay, shortly to come here. Let's consider an example before we get to the vector field though. Let's take the mass to be 1 kilogram. Let's take K to be 13 newtons per meter. And let's take B, negative B is the constant of proportionality for the friction, to be 4 newtons per meter per second. It's because that is proportional to the velocity, is why the units are the way they are. Let's also suppose the initial position is 1 meter and the initial velocity is 0 meters per second. So I've grabbed that mass, I've pulled it a meter to the right, and now I'm going to let it go from rest. Assuming it doesn't hit the wall, make sure the wall is far enough away, what will the motion be? Well, I'm not going to show you in this lecture how to find the unique solution. That will be shortly to come. But it turns out that the unique solution is this parametric vector, this vector-valued function of t. We will check it here in a second. Careful here. I do have some fractions that you won't notice unless you're careful in looking at this. Y of t, the position as a function of time, is e to the negative 2t times cosine of 3t plus really 2/3. I got a 3 over there. Make sure you don't miss that there. 2/3 e to the negative 2t times sine of 3t. Or if you prefer, 2e to the negative 2t times sine of 3t, all divided by 3. And the second one, the velocity, which is the derivative of y, you can check that, take its derivative and simplify, you actually do get this. The cosine terms go away. You got to use the product rule and the chain rule, and be careful. This is really negative 13/3 times e to the negative 2t times sine of 3t. This can be rewritten as a linear combination, if you like, of two linearly independent functions, vector valued functions. Now, just 5 minutes ago, I talked about linearly independent scalar valued functions as not being constant multiples of each other, and that would mean the graphs are not vertical stretches or compressions of each other for the horizontal axis. But these are vector valued functions. You can't think that way in terms of the graphs, but you can say, hey, these are not scalar multiples of each other. There's no scalar I could multiply this function by to get this function, and vice versa. So they are linearly independent in that sense. That's what linear independence means for two functions, and in fact two vectors in Rn. They're not scalar multiples of each other. We can check that this works. Let's do that now. How? You tell me, right? We always talk about this. Left-hand side equals right-hand side. Does it for this function, and we also will check the initial condition. Here's the derivative, okay? Focus on the relationships here. I need to differentiate this d dt. To get this, I'm effectively doing what I told you to do a minute or two ago. Use the product rule and the chain rule. On the first term, I've got a product e to the negative 2t times cosine of 3t. This term here is the derivative of e to the negative 2t. Note the extra factor of negative 2 from the chain rule times the second function, derivative of the first times the second, plus the first e to the negative 2t times the derivative of the second. The derivative of cosine of 3t would be negative 3 sine 3t because of the chain rule. These two terms are what you get when you differentiate that part. Take the derivative of 2e to the negative 2t, say, over 3. Get an extra factor of 2 and a negative sign. You get a negative 4 over 3e to the negative 2t. Keep the sign of 3t the same. Then, so that's the derivative of the first times the second. Now take the first, 2e to the negative 2t, times the derivative of the second. Say sine of 3t over 3. That derivative is cosine of 3t over 3 times 3. And the 3's cancel because of the chain rule, giving you this. Once again, the product rule is necessary for the other one as well. Going down there, I'll let you check that. Now simplify. Notice that the top does simplify to this, which is the same as v. Right away you can see that the derivative of y with respect to t is the velocity. Does it simplify? Yes. Just double check it. For example, these two things completely cancel. And with the sine terms, the coefficients, the they're like terms, we got to look at the coefficients. Negative 3 minus 4/3 is negative 9/3 minus 4/3 is negative 13/3, which is what you see there. And we can leave the second one as is. That's the left-hand side. What about the right-hand side? The right-hand side is this matrix times y of t, this one, times this. Go ahead and do the matrix times this vector. Okay? In other words, for the first component of the answer, take the dot product of this row with this column. 0 times this plus 1 times this is going to give you just that, right? Same thing as that. Same thing as v. For the second one, you'll get negative 13 times this minus 4 times this. Use parentheses to make sure you don't make mistakes. If you check it, I'll go ahead and leave that to you. You will get what you see here. And these two functions of t are the same. This does check. What about the initial condition? I guess I didn't do that here. I thought I did. Let's check the initial condition. Boldface y, or vector y, of 0. Here's the formula up here. Plug in t equals 0. E to the 0 is 1. Cosine of 0 is 1. Sine of 0 is 0. This term goes away. Looks like we're left with a 1. Plug in 0 down there, you get a 0. And that is the same as the initial position and the initial velocity. Y0 equals 1, V0 equals 0. Here is a graph of the solution as a parametric curve in the phase plane, where y is horizontal and v is vertical. Here it is. And arrows indicating the direction of motion. This is a parametric curve going toward the origin, spiraling, in fact, toward the origin. And this spiraling actually technically goes on forever and ever, although it's really tiny spiraling as you get closer and closer to the origin. That should make sense. You've got, in fact, cosines and sines, and you also have exponential decays. It should make good sense that this goes toward the origin as t goes to infinity. Is the origin an equilibrium point? It is. We'll talk about that. And so, at least with this solution, it seems to be some sort of spiral sink. And in fact, we will look at the phase plane, the vector field, and the solutions in that vector field. And we will see it is like it's spiraling toward the origin. All the solutions spiral toward the origin. And it therefore would make sense to say the origin is not just a sink, but you might say a spiral sink. Pretty cool. What's the vector field? It's a function from the plane to itself, called boldface f, as we will typically write with vector fields, defined by this formula. Vector fields take point inputs, write them as points, and give you vector outputs, write them as column vectors. Although, you don't have to. You could write this as a column vector, but just keep in mind that it's good to think of the inputs as points and the outputs as vectors because of the way we draw the vector fields. We attach the output vector at the given input point for all points in the plane in theory, though in practice you need to do it just at finitely many. For example, what is the vector assigned to the point or attached to the point whose coordinates are y comma v equals 0 comma negative 2? Plug in y equals 0 and v equals negative 2 into this formula here. You'll get this, right? If v is negative 2, this becomes a negative 2 there, which is what you see there. If y is 0 and v is negative 2, you get a 0 minus 4 times negative 2, which is positive 8. That is the output vector when the input point is the point 0, negative 2. Let me draw this on the board relatively accurately. Then I'm going to show you some computer output very soon. That's, well, some's accurate and some is not. You'll see what I mean when we get there. The point 0, negative 2 is this point right about there. The vector that would get attached to that would have its tail at that point, has components negative 2 and 8. In other words, its horizontal displacement is 2 units to the left, And its vertical displacement is 8 units upward. So I need to go 1, 2, and then 6 more. 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. The vector in the vector field that is attached to this point looks about like this. Hard to draw it straight. Okay? That point is the point 0, negative 2. Y equals 0, v equals negative 2. This vector right there is f of 0, negative 2. It has components negative 2, 8. It points to the left. That's why the first component is negative, and it points upward. That's why the second component is positive. And if you remember the solution I showed you a few minutes ago, that should make sense, since solutions need to follow the vector field. Just like scalar differential equations, the solutions need to follow slope fields. Here's the vector field, almost. I decided I needed to divide by 5. It's the vector field divided by 5. And again, like before, Mathematica wouldn't let me write that as a column vector. If I'm writing it by hand, I'd write it this way. Dividing by the vector by 5 really means multiplying it by 1/5. Why did I do that? Because it makes the vector shorter so we can actually get a nice picture. When you have the actual vectors themselves, they're all so long that the picture's not so nice. The one I drew on the board corresponds to this one right here. That one, if you continued it to have the right length, which would be 5 times longer, would go up to about somewhere right about there at negative 2, 6. That would be 5 times the length of what's actually drawn here, attached to the point 0, negative 2. So you see the vectors having some sort of rotation, you might say, going on clockwise around the equilibrium point at the origin. Why is the origin an equilibrium point? Because when you plug it into the formula for the vector field, you get the 0 vector. Plug in y equals 0, v equals 0, you get 0, 0, the 0 vector. Just a big dot at the origin. Don't draw it to have any length. Make it big just to emphasize it, just to say that's an important point to think about. Of course, points don't have any area. I'm making it big just to emphasize it. Remember that solution curves follow this in such a way that whenever they pass through one of the tails of one of these vectors, that vector has to be a velocity vector for the solution curve at that point. So that means it's got to be tangent to the curve. That green arrow right here has got to be tangent to the curve at this point, and have a length, well, at least if I multiply it by 5, equal to the speed of motion, the instantaneous speed of the motion of the curve at that point. Now that speed has nothing to do with the speed of the mass in the spring. I shouldn't say nothing, but it's not equal to the speed or velocity of the mass in the spring. It's just related to it. It's the second coordinate of points that gives you the velocity of the mass in the spring. So it moves, these things move fast when the vectors are kind of long. As they get close to the origin, those vectors get shorter. And so the parametric curve, as you keep graphing it for larger and larger values of t, slows down as it approaches the origin. The vector field is very close to having the 0 vector for output when you are very close to the origin. Yes, solution curves must follow or obey the vector field. Why? Because of the nature of the differential equation. We're saying solutions have really velocity vectors, dy dt, dv dt, that equal the output of the vector field at any given moment in time, wherever you happen to be along the solution curve. You get the idea? A solution curve, no matter where you are on that solution curve, whatever the moment in time is, the vector in the vector field is the velocity vector for that solution curve at that moment in time. It points tangent to the curve at that moment, and its length equals the speed of the curve as it moves through the plane. Generate solutions that look like this. These blue arrows, notice, do have some curvature to them. They're not true vectors. This is just Mathematica's way of drawing in solution curves, essentially. You can make it with something called StreamPlot, which I will show you. And you can see the solution curve spiraling in toward the origin, no matter what the initial condition is. Makes sense. You got friction. No matter, How crazy that back and forth motion is at first, it should settle down toward equilibrium. That's what the friction does. This is something called the direction field of the vector field. Essentially what we do here is take all the vectors in the vector field, which are really the green vectors, most easily seen over here, and normalize them. Find unit vectors in the same direction and draw all of those. Now actually Mathematica didn't draw these to be unit vectors, it made them a bit shorter, just to make the picture look nicer. So these are a bit shorter than unit vectors, but they all have the same length. They help you focus on the direction of solutions, not the speed. So we might have a solution, for example, that looks about like this. Just trying to draw solutions to follow the vector field. Of course, it's impossible to draw these things perfectly. Just do your best, do a reasonable job. And I can do that no matter where I start for my initial point. What about the Nullclines? They can help you draw solutions as well. I talked about Nullclines. I introduced them in lecture 14a. In general, when your differential equation systems, your system involves x in the first equation, dx dt I mean, and dy dt in the second equation. There's an x nullcline and a y nullcline. The x nullcline is the curve or curves where dx dt is 0, and the y nullcline is the curve or curves where dy dt is 0. But in this example, we've got dy dt in the first equation and dv dt in the second. So we've got a y nullcline and a v nullcline. Y is horizontal, v is vertical in this setup. The y nullcline, the first nullcline, is where the first right-hand side function equals 0. The first right-hand side function is f of yv equals v, remember? That's the first right-hand side for the system of differential equations, dy dt equals v. Essentially set that equal to 0. What's the set of points where that's 0? That's why we call it a nullcline. 0 curved line. These are actual lines. It's the set of points in the plane where v is 0. Y-axis horizontal, v-axis vertical. V is going to be 0 along the y-axis. That's where v is 0. That'll be our first nullcline, our y nullcline. That's where solutions cross with vertical tangents, either going upward or downward, because the horizontal component of the velocity vector for the solution curve is 0 there. The v nullcline, the second nullcline in the setup, is found by setting the second right-hand side function equal to 0. Set this equal to 0. That set of points is the v nullcline. It's probably helpful to solve this equation for v as a function of y. Not y as a function of v, because y is horizontal and v is vertical. So it's best to solve for v as a function of y. I mean, you could do it the other way, but that'll be more confusing, because it's not what we're used to. Solve for the second variable as a function of the first variable. V is a function of y in this case. So I'd set this equal to 0. I'd add 4y to both sides. 4v, excuse me. 4v would be negative 13y. Divide both sides by 4. I get v equals negative 13 force y, which is the same as v equals negative 3.25y. So the v nullcline, where dv dt is 0 and solutions have to cross horizontally, left or right, is going to be aligned to the origin with a slope of negative 3.25. Here are the nullclines. So the blue one, that's the y nullcline, where v equals 0. And the red one, that's the v nullcline, where dv dt equals 0. And that again is equivalent to v equals negative 3.25y, aligned through the origin with the slope of negative 3.25. Notice when y is 1, we are down at about negative 3.25 there. I've drawn the direction field on there. Notice the arrows when the base, the tail of the arrow, the vectors, are on the red line. The vectors point horizontal. This vector here is pretty close to horizontal. I know they're small. I hope you can see them okay. This one's close to the horizontal. This one's pretty close to horizontal. And when you cross the y nullcline, you have to cross vertically. It plotted a bunch of vectors down here to cross it vertically with those vectors, those arrows right out, vertical pointing downward. These ones over here are vertical pointing upward. When you try to draw the solution curves more carefully, you should cross the y nullcline vertically and the v nullcline horizontally. And by continuing to do that kind of process, you're forced to head toward the origin, really. Emphasizing the origin as a spiral sink. Here's the direction field, nullclines, and solutions in light blue. Again, notice these light blue arrows are curved arrows, they're not true vectors. They're supposed to represent solutions. It's kind of hard to see. I can do my best to follow one of these. This one here goes like this. Head toward the origin actually pretty fast because of the exponential decay. But in theory, it does spiral around and around forever and ever. In the mathematical model, the oscillations happen forever and ever so slightly. Does that happen in reality? I'm guessing that's actually probably where the model breaks down. I'm guessing eventually it truly comes to rest. And maybe not even eventually, like in a long time. It probably comes to true rest in a short amount of time. The mathematical model doesn't predict that, though. All right, so that's almost the end of lecture 15A. Let's end with Mathematica. Let's go take a little bit more time to go through this a little more slowly than usual. DSolveValue is my favorite way of solving differential equations when they can be solved. There's also just a plain DSolve instead of adding on the word value there. But the output for DSolveValue is a little nicer. It is a built-in Mathematica function or command. It's got square brackets around its input. Its input consists of three things in this case. The differential equation, the function we're trying to solve for, and an emphasis on what the independent variable is. This was my second order scalar differential equation. Y double prime, same as the second derivative of y with respect to t twice, plus 4 dy dt plus 13y equals 0. You need double equal signs in there when you are solving equations. If you put a single equal signs in there, it's going to mess things up, okay? Make sure you don't forget the double equal signs. Even though we don't write the of t's by hand in Mathematica, you need to put the of t's with square brackets. Comma, then again the function you're solving for, comma, then an emphasis on what the independent variables. This is going to give us the general solution because it has no initial conditions. Switched around the roles of C1 and C2. I don't know why I did that, but it's not a big deal. e to the negative 2, C2, we would probably put the C2 in front, cos 3t plus e to the negative 2t, C1 sine 3t. E to the negative 2t, I'm not sure if I said that right. That's a general solution. And based on initial conditions, like y of 0 equals 1, the initial position is 1, and y prime of 0 equals 0, we could solve for C1 and C2 by hand. And do what this next line is going to do to give us the unique solution of the IVP. Notice now that in this first input for DSolveValue, I've got the differential equation, comma, the two initial conditions, again with double equal signs. Notice those are inside the curly braces because this sort of goes as a unit together. It's an IVP. So the curly braces emphasize that. Then put a comma, then put your solution function that you're trying to find, then put a comma, then the independent variable. I think it's unfortunate, but when you do this, the output is not ideal. It doesn't multiply the 1/3 e to the negative 2t through there. I think that's not a good thing. You can fix that. You can do a postscript operator of expand at the end to multiply things through. Although here I'm doing it in vector form. Let me redo this in scalar form. There we go. There's the unique solution as a scalar function. Yeah, that is the same initial value probably as before. All of a sudden feeling like it's maybe not the same answer. Does it match this? Yes, it does. Okay. All right, there's our scalar solution. If I do it as a system, which I can do, I add an extra function in there, v, the velocity. Y prime equals v. V prime equals negative 13y minus 4v. That's the system. Now write the initial conditions as y of 0 equals 1 and v of 0 equals 0. Solve for both y and v. And expand the answer. And you see what you get what you see there. Inside curly braces, technically speaking, such a thing is called a list in Mathematica. But we can think of it as a vector, with the first component here and the second component there. Or a point. Doesn't matter. You can think of it either way. I can now define capital Y of t to be that function of t, and it is a parametric curve. I can plot it with ParametricPlot. ParametricPlot right there inside the show will graph the parametric curve. The other stuff, this graphics, red arrowheads, etc., arrows, that's going to graph some arrows in the picture. The show combines the graphic objects, the parametric plot, and the graphics that are going to graph some arrows. All this stuff is just formatting to make it look nice. And here we have the picture that I showed you in the PowerPoint of the solution curve. And the arrow commands inside graphics draw these little arrows in there. This one, because it's in a manipulate, will make an animation. See the manipulate? I've got a parametric plot in there. Just a parametric plot, in fact. This all is the parametric plot right there with various formatting commands. It's inside the manipulate. After that, you put a comma, and then you put the animation parameter for the manipulate, time in this case. I'm going from essentially 0 to 2 pi over 3. I put a number slightly bigger than 0 there because in the parametric plot, whose variable I'm calling u, it starts at 0. So if I put a 0 there and a 0 there, it won't plot anything. So I need to put something slightly bigger than 0 right there. This appearance open just helps me see that what t is. The label style large just makes t bigger in the animation. And here is the animation showing the curve as time goes by. And do notice the actual motion of the curve itself, the point, is fast at first, slows down, and keeps slowing down as you get closer and closer, as I mentioned. Although it is actually a little bit subtle here. It goes fast at first, and then it slows down near this curve, and then it actually does speed up a little bit in here before slowing down again. And that can be emphasized if you add a velocity vector into the picture. Pink vector is essentially a velocity vector divided by 3 in length. So it's 3 times shorter than it should be. Pretty long at first, then it gets short, then it gets a little longer again, then it gets shorter and shorter. And now you really can't tell how long it is when you're so close to the origin there. The vectors are so short that you're just only seeing the arrowheads themselves. But they are pointing in the direction of motion for the black dot, but the pink one is at least. The red one is a position vector for the black dot. The pink one is a velocity vector for the black dot. It's always tangent to the curve. It has a length equal to the speed at any given moment in time. A few more things to show you here quick. Don't worry about this code. It does make this picture. I'm not going to emphasize that code so much. What I do want to emphasize is how to make a StreamPlot. This code right here uses a built-in command called StreamPlot. Right there. This is the vector field which I defined earlier, back up here. Right here, actually. I should have kept this separate. I'm calling it f-damped because it's a damped model. Putting f-damped into the StreamPlot will make these light blue curves that are supposed to represent solution curves. I can show that. I gave that a name. I call it StreamPlot here. I also gave this graphic a name called damped vector field. I can show those together, damped vector field, StreamPlot, together in one picture here, showing the vector field and the solutions. And I can also do it for a direction field. Here's the essential code that makes a direction field. Although I am noticing that the picture looks different than what I got in my computer. My computer's version of Mathematica is newer, and it actually colored the arrows. This one is not coloring the arrows, so you don't see the exact same picture as before. But I can show these things along with now the Nullclines as well. Yeah, how do I make the Nullclines? I essentially just plot those two functions of y, one of which was the zero function, which is the horizontal axis, and one of which was negative 3.25y. V was negative 3.25y, gets this red graph there. That plots those Nullclines, and the show combines them with the other graph that I call the direction field to give you this picture, and we can also add in the StreamPlot as well in this right here in the show. So I still had to go kind of fast there. As usual, I make these kinds of things available in my Google Docs folder, and you can certainly download these things and experiment with them if you want. Thanks for watching Lecture 15A.